Hi guys, today I have with me a forces elevator problem. Not gonna lie, I actually hate these problems, but well, I hate forces in general, but it's part of physics, so I'm gonna do a bunch of tutorials. I actually really like kinematics, but that's over. I think I really beat it to death because my views have started to go down, but that's okay. So now it's gonna be forces and then energy is after this, and I love energy. So I'm excited for that, but we have to get through a bunch of forces questions first. Okay, so before I get started on the actual problem, if you like my videos, don't forget to like and subscribe, please, because I have started getting some hate comments. And I think that's actually pretty cool because it means that, if I have, like, I've gotten a few fan comments and I've gotten some hate comments. So I'm I feel like I'm in the YouTube atmosphere now because I think you haven't really made it until you have haters, right? Okay, so if you want to support me, feel free to leave a nice comment and a like and subscribe, please. Thank you so much. Okay, so let's get started on this question. You walk into an elevator, step onto a scale, and push the up button. You recall that your normal weight is 625 newtons. Draw a free body diagram. A, when the elevator has an upward acceleration of magnitude 2.50 meters per second, what does the scale read? B, if you hold a 3.85 kilogram, 3.8 did I say that right? Okay, 3.85 kilogram package by a light vertical string. What will be the tension in the string when the elevator accelerates, as in part A? Okay, so let's sort of talk a little bit about these elevator type questions. And not gonna lie, like these always confused me in undergrad. So I thought maybe we can just go through some of the like light theory of it or like I guess like the basic concepts, and then we can actually do the problem right after that. Okay. So when we're in an elevator, there are sort of three major scenarios that can happen, right? So either you are completely at rest, right? So you're either at rest, you're going up, or you're going down, right? And I'm assuming this is like a one-dimensional elevator that goes up, down, and stops. I'm not really thinking about any elevators that move side to side. Okay, so those are the three possibilities, right? So I'm just gonna go ahead and draw like a little elevator contraption right over here. And then what we can do is we can go ahead and draw a person in these elevators, right? So that's one person. Let me just draw that a little bit neater, nicer and neater. Okay, maybe I can just do like that. Okay, not a huge fan, but whatever. Okay, there we go. No, I hate that. Let's try again. Okay, better, but not the best. Okay, doesn't matter. This is not an art class. Okay, and that was so cliche of me to say, but okay. So when we're at rest, we have what are the forces that are acting on this person, right? So there's Fg, which is the force of gravity, right? And then there's the normal force, right? When we're going up, there's also Fg, and then there is the normal force, right? And then same with going down, there's Fg, and then there's the normal force. Okay, but what's the difference? The acceleration is the difference, right? So when we are at rest, the acceleration is 0. When we're going up, the acceleration is, upwards. And when we're going down, the acceleration is downwards, right? It's going to be like negative, right? So what I mean is it's, going to be the same direction as gravity. And this one is going to be opposite direction as gravity, right? So, and I'm just going to go ahead actually just do a little positive and negative scale right there. No, that's not, okay. Yeah, that's what I wanted. Perfect. Okay. So now let's use our forces equations to come up with an equation for these three scenarios, right? So we know that the sum of the forces, right? The sum of the forces is going to be Fn, right? Because that's upward, so it's going to be Fn minus Fg, right? Because Fg is in the negative direction. And that's going to be equal to Ma, right? And Ma is 0, so that's going to be Ma or 0, right? So in this situation, Fn is equal to Fg, right? So the normal force is equal to the gravitational force. That makes sense. That's not too hard to grasp, right? But, in this situation, when we are going up, right? Again, we have our summation of forces, and that's going to be Fn minus Fg. And now it's going to be equal to m times a, where this is some sort of, positive value because it's upwards. And that means that our normal force is going to be ma plus fg, right? So that's going to be our normal force. So our normal force is going to be the acceleration, the mass times acceleration of the acceleration we're experiencing, plus the force of gravity. Okay, our normal force in this final scenario, in which we're going down, is going to be summation of forces is equal to Fn minus Fg, right? And over here, it's going to be, this minus Ma, right? Because it's going to be downwards. And here, this means that Fn is equal to, Fg minus Ma. And that's our final scenario. So these are the three situations in which we're going up, we're going down, and we're at rest. And that's sort of how our normal forces are going to look like. And why normal force? Because, in the question, it's asking your normal weight, right? So when we stand on a scale, right? So you probably heard that your mass is not your weight, right? Because your weight is your mass times gravity, and your weight would be different on the moon and your weight would be different on Earth because they have different gravitational forces that are acting on a person. But yeah, so that would be different. But mass, that's going to be the same. You are going to be, for example, if you're 50 kilograms, you're 50 kilograms on planet Earth, you're going to be 50 kilograms on the moon. If there is a planet, 68 million light years away, you're going to be 68 kilograms on that planet. So that's never going to change, but your weight does change. And in an elevator, when you're accelerating up or down, plus you have, gravity as well, then your normal weight, right? That's going to be different, as we've illustrated in these diagrams right now. Okay, so now that we've established all of this, let's go ahead and get to the actual questions, but let's keep these in mind. And I'm just going to go ahead and just take note of these on my paper, and you can do the same. So when at rest, just so that I can rewrite these again, and I don't want to make any mistakes when I'm rewriting this down. Going up. And then we have Fn is equal to Fg minus Ma, and this will be going down. Okay, perfect. Okay, so I'm gonna erase the screen right now. Perfect, okay. So when we do that, what's going to happen is that, let's get started with the actual question first. Okay, so you walk into an elevator, step on a scale, and push the up button. So right now, which scenario are we focusing on? We're focusing on the up scenario. So when we are going up, right? When we are going up, then we said that normal force is going to be equal to Ma plus Fg. This is going to be our equation for this scenario. Okay, so recall that your normal weight is 625. So normal weight means that I think I've been conflating, the term normal with normal force. No. Normal weight here means that, like, it means that without an elevator, right? So without an elevator, so normal weight, which means at rest, is, at rest. And that is going to be Fn is equal to Fg, right? So this is a situation of like what you would experience like pretty much anywhere on Earth that's not an elevator. So if you're just in your room, in your bathroom, wherever, right, you're going to stand on a scale. It's going to be Fn is going to be equal to Fg, right? So if that's the scenario and our normal weight is 625, then that means that if we have Fn is equal to Fg, that's going to be equal to mass times, our acceleration due to gravity on Earth. And we know that that's going to be mass times 9.8 meters per second squared. And that is equal to 625 newtons, right? So that's 625 newtons. Then all we have left is to solve for mass. 625 newtons divided by 9.8 meters per second squared. And that is going to be equal to, according to my calculator, I'm just going to redo this because I sort of did this question really roughly. I don't have like an actual plan written out, so hopefully it goes right the first time. So this is 63.78 kilograms, right? So that's the weight, sorry, that's the mass of the person, right? So that's the mass of the person that is in this elevator. Okay, so I'm going to write that down right next to this going up equation. So these are going to kind of be my given. This is going to be my given line, right? Anything in light green is going to be the given, and that is mass is equal to 63.78 kilograms. Okay, so now let's get started on A. When the elevator has an upward acceleration of magnitude 2.50 meters per second squared, what does the scale read? The scale is going to read Fn, right? It's going to be Fn, which we have the equation for. I'm just going to go ahead and erase this so we can get started on part A. Okay, so for part A, let's write down all of our givens, right? So we have, draw a force body diagram. So we sort of already did that, but let's just do that again. So, if this is our, I know force body diagrams are usually with like squares or boxes, but I'm just going to do this with a dot. So that is going to be like our person in an elevator. This is Fg, and this is going to be Fn. And we said that this is going to be positive, this is going to be negative, and I'm just going to go ahead and say like acceleration is going to be this way, right? That's going to be acceleration. Okay, so when the elevator has an upward acceleration of 2.50 meters per second squared, I'm going to write that down in my givens. And that is going to be, so mass is equal to 63.78 kilograms. Our acceleration is going to be 2.50 meters per second squared, or our acceleration due to gravity is 9.80 meters per second squared. And that is really essentially everything that we need for this question. So Fn, right, so we have our equation right there. We want to find out what the elevator, what the weight, the scale reads. So Fn is equal to ma plus Fg. And Fg, right, I know I never wrote this out explicitly, but it's just mg. That's our equation, is equal to ma plus mg. And ma plus mg, we have everything right over here in our given, so all we really have to do is plug it in. So I'm just going to write this as m times a plus g, and that's going to be 63.78 and 2.50 plus 9.80. And this is going to be, if we multiply this together, I'm getting a total of 784.4 newtons. All right. Okay, so that's our answer for part A. When the elevator has an upward acceleration of magnitude 2.50 meters per second squared, what does the scale read? It reads 784.4 newtons. Done. That's part A. Okay, part B. If you are holding a 3.85 kilogram package by a light vertical string, what will be the tension in the string when the elevator accelerates, as in part A? Okay, so let's go ahead and erase all of this. I'm just going to go ahead and keep the givens because I feel like that's not necessarily going to change too much, and I can just fill in what does change. Okay, so now I'm actually going to go ahead, and if we look at this diagram right over here, I'm not going to lie, this holds pretty true, but that's for part A. Part B is almost identical. So let's say this is the package, right? This is the package, right? What are the forces that are acting on it? Gravity, obviously, right? Because it's not just like floating, like it's not, you know, just still in the air. Gravity is working on it, right? And then this situation, right? So we have this like string, and that means that there's going to be tension, right? There's going to be Ft, and that's pointing upwards, right? And that's according to Newton's law, right? Where every like force has an equal and opposite, or every action has an equal and opposite reaction, right? And in this situation particularly, it's because, you know, like this, let's say it's like a ball, right? Or sorry, again, like it's package, right? It's gravity's pulling it down. If there were no other forces acting on it, then it would just keep moving downwards, or it would be in free fall. But no, there's actually a string that's making sure that it's not in free fall, and therefore then there is this equal and opposite tension on this string that is preventing it from, you know, being in free fall. So it's opposing this gravity, and that's why it's in the opposite direction, and that's why it's tension. Okay, so we have a force of tension and we have a force of gravity, and they are opposing each other. But, you know, in this situation, if we can figure out, we're going to have, oh, we also have our acceleration too, right? So we have our acceleration, and this is going to be accelerating upwards because, again, we are in this elevator. And if we weren't in this elevator, then it would just be Fg is equal to Ft, like in our, you know, in our no acceleration scenario, but there is acceleration. So it's going to be accelerations upwards. So we can actually use the same ideas as in part B, as in part A, right? So we have our mass, which is equal to 3.85 kilograms. Our acceleration is going to be 2.50 meters per second squared, and our gravity is going to be equal to 9.80 meters per second squared. But hey, we can't really use this equation right over here, right? Because this is Fn. So we need to come up with a new equation for part B. So it's going to be really similar, right? So we know that, like, for example, what is going to be Ft, right? So if we want to write an equation in terms of Ft, not Ft, sorry, we could actually no, what's better is this right over here, the original equation we were writing. So we want to write the summation of forces. If we want to write the summation of forces, it's going to be, again, Ft is in the upward direction, so that's going to be Ft minus, minus Fg, right? Because that's in the opposite direction. It's in the negative direction, and that's going to be equal to m times a, mass times acceleration. And I mean, I could do this, but my vector, I didn't put vectors everywhere, but you know, not too important right now. Not the point of this video. Okay. Anyways, so now if we want to solve for the tension in the string, we just need to isolate for Ft. So Ft is equal to Ma plus Fg. And, this looks pretty much identical to this equation right over here. And all we're going to do now is we're going to plug in our values. So Ft is equal to Ma, right, which is 3.85 times 2.50 meters per second squared. I didn't write units for this again just because I don't have space, but you should probably do that. It's good practice to do. Plus Fg, which is going to be 3.85 kilograms times 9.80 meters per second squared. Okay. And when I plug in all those numbers into my calculator, what I'm getting is 47.4 or 355 or 47.4 newtons. That is our tension in the string. Okay, perfect. So that brings us to the end of the question. What will be the tension in the string when the elevator accelerates, as in part A? It's going to be 47.4 newtons. That's going to be the tension in the string. Thank you so much for watching. If you have any questions, I love reading your questions, comments, concerns. Please feel free to send me an email, or even better, leave it in the comments in this video below. If you like this video, if you thought it was helpful, please don't forget to like and subscribe and share with your friends. If you don't find it helpful, I'm sorry. I hope you find one of my other videos helpful. And if you have any, constructive criticism, I'm happy to hear that. So you can leave that in the comments as well. Anyways, well, it depends on the constructive criticism, but if I'm being honest. But yeah, if you have something that would help you understand these problems more, then yeah, tell me, then I'll try to incorporate it. But if it's like you need to talk less, sorry, I can't do that. Thank you very much for watching. See you next time. Bye.